The title of the talk is Non-Euclidean Erdős Anning theorems, and I will explain that. But basically, it's about points with all the distances between them being integers. And so I thought I would start with some examples. So in one dimension, it's super easy to find points at integer distances. You just use all of the integer points on the real line, and their distances are integers from each other. I'm going to be talking about spaces that are not flat. And so you can't actually make a one-dimensional space that's not flat. They're all topologically equivalent if they're geodesic spaces, but you could think of any curve and the distances along that curve and place points at unit distances along that curve, and you would have exactly the same distance structure. And this is what, for instance, the Romans did long ago by placing milestones along their roads. So this is kind of the canonical example of an infinite set of points at integer distances from each other. Now, if you want to go to two-dimensional point sets with integer distances from each other, again, it's easy if you just want a finite number of points. If, for instance, any three integer distances, as long as they satisfy the triangle inequality, will be enough to define an integer triangle, 3 points at integer distances from each other. And, you know, since ancient times, people have studied right triangles at integer distances from each other. Now, we don't need the triangle to be a right triangle in order to have integer distances, but if we have many integer right triangles, we can put them all together into one picture. Scale the triangles so that all of them have a unit length side, and then place the other side along the x-axis, place the unit side along the y-axis, place them all together like this. All of these distances to this top point will be rational because you scaled them by a rational amount. All of the distances between 2 points on the axis will be rational because they are the differences between two rational numbers. And so we have infinitely many points with rational distances that are not all on one line. There's one of them that's not on the line. And you could put another copy of this top point reflected across the axis below the line, and now you have 2 points that are not on a line and everything else on a line. So not quite everything all on a line, but close. Now, it should be not much of a surprise that Leonhard Euler was interested in. Can you see these? Do I need to move this off screen? Would that be better? Let's move this down here.
We do see your cursor.
You can see my cursor, but not my Zoom windows. Okay, what I'm seeing is my, that's better.
Perhaps you're only sharing.
Zoom was covering part of my slides. Leonhard Euler was interested in extensions of the Pythagorean theorem, as were other mathematicians before him, Fibonacci, for instance. Here's a famous open problem coming from the work of Euler. We don't know if it's possible to make a cuboid with right angles, integer side lengths, integer face diagonals, and an integer body diagonal. You can make 6 of these 7 quantities be integers, but we don't know how to make all 7 of them integers. So that's a famous open problem. Another observation of Euler that's also closely related to this question of what point sets can have integer rational distances is this construction, that there exist infinitely many points at rational distances from each other on a unit circle. And one way to do that is to again use a 3, 4, 5 right triangle, scaled so that the hypotenuse is 1, and repeatedly reflect it across one of its sides to another point on the circle, to another point on the circle, to another point on the circle, keep going around. Because this angle is irrational, it's not a rational multiple of pi, you can keep going around and you'll never repeat the same point twice. But all of these points on the circle and the center of the circle have rational distances from each other. And so this gives you an infinite set of rational points, of points with rational distances to each other. And actually, no 3 of these points are collinear. So it's very far from being all on a line, but somehow it's all on a circle. It's still very constrained. And in fact, this question of can we get points with rational distances that are not all on a line and not all on a circle is still quite open. So there exist sets of 7 points in the plane. Here's one of them from these references, where all of the distances are integers or rational numbers. We do not know if there are more than 7 points in general position with no 3 on a line and no 4 on a circle that have integer or rational distances. 7 is the most we know. So it's a hard problem. It's an open problem. It's not a problem that I'm going to address, but it's related and it's important. Now, maybe something much different from that is possible. Erdős and Ulam speculated, I wouldn't call it a conjecture, because as far as I know, what Ulam was trying to come up with in this proposal was, what is the craziest thing that could happen? Can we manage to prove that that crazy thing cannot happen? And the craziest thing he could think of in terms of rational distances in the plane, very far from all being on a circle, very far from all being on a line, is maybe there's a dense subset of the entire plane where all of the points in that subset have rational distances from each other. It seems unlikely. It would disprove some major conjectures in mathematics unrelated to discrete geometry. But we don't know how to prove that it's not true, except maybe addressing it by these other bigger conjectures. So that's the Erdős-Ulam problem, and it's also unknown. What we know is that we can find infinitely many points on a circle +1. We can find infinitely many points on a line +2. And there are some sporadic finite examples. But those examples of infinitely many points on a line +1, infinitely many points on a circle +1, have rational distances. They don't have integer distances. And that actually is an important difference. It doesn't sound like much, rational, integer. If you have a set of finitely many points with rational distances, then you can just scale them to get the distances to be integers. Find a largest common denominator of all the distances, scale them by that scale factor, the distances turn into integers. But that gives you arbitrarily large subsets of the circle, for instance, with integer distances, but it does not give you infinite sets of points with integer distances. Because the more points you add to your set, the bigger the scale factor you need. And so there's not one common point set with all the distances integers, infinitely many points. And so that is the subject of the Erdős-Anning theorem. Is it possible to get infinitely many points with integer distances that are not all on a line? The answer is no. Erdős and Anning and Erdős proved in 1945 that if you have a set of points in the Euclidean plane with integer distances, then either it's all on a line, the set we started with, the integers on the real line, or it's finite. Those are the only things that can happen. I've looked at their proof. It's not that enlightening, but in the same year, in the same journal, Erdős by himself published a one-page paper proving the same thing, proving a little more strongly that if you have a set of points in the plane with diameter d and they're not all on a line, then there are only O of d squared points. That has since been improved to sublinear in d, but Erdős gave a 5-line proof. It's a very short, simple proof. He wrote that an analogous theorem holds in higher dimensions. He didn't specify any details. And so that is the proof that I'm going to start with. And this is the theorem that I'm going to be discussing. The question is that I'm addressing in this work is, can we get similar results in other metric spaces? Because the Euclidean metric space, it's nice. We can prove lots of things about it, but maybe we can generalize this to other metric spaces. I started out looking at the hyperbolic plane, for instance, but there are many other less uniform metric spaces for which similar results might plausibly be true, and for which, in fact, I can prove that they are true. But in order to get there, I want to go through Erdős's 5-line proof and then go through a different proof of the same theorem that is more flexible, allows me to generalize it to other metric spaces, but I will start out with the Euclidean metric space. So this is the main idea, not of my paper, but of Erdős's paper. If you're given 2 points that are at integer distance d from each other, A and B, and you want to have some third point C that is supposed to be at integer distances from both A and B, then C has to be on one of these curves. The distance from C to A and the distance from C to B, those two distances cannot be very different from each other. They have to be within d of each other by the triangle inequality. And so you can ask, what is the difference between those two distances? It might be as much as, in this example I've drawn here, the distance between A and B is 3. So C could be, or I guess I've labeled it X in this figure, could be as much as 3 units farther from B than A. And if it is, it's on this ray, vertically extending in the other direction up from B from A. The two distances could differ by 2. And then you get this branch of a hyperbola. The same hyperbola is over here, but giving a different branch for the points that have difference too, but in the other direction, closer to B than to A. And all of these curves, for each possible integer difference between the two distances from X to A and X to B, for each of those differences, we get a hyperbola, a branch of a hyperbola. The two opposite rays that you can see here, you can think of them as being a degenerate hyperbola. So if we have 2 points, then we know that any third point with integer distances has to be somewhere in this system of hyperbolas. If we have 3 points, A, B, and C, that are not all on a line, then we get these 2 systems of hyperbolas. One for A and B, say, another system of hyperbolas for B and C, where the number of hyperbolas in this system, including the degenerate one, is the number of possible differences between the two distances, which is at most d plus 1. And any point that is going to have integer distance to A, integer distance to B, and integer distance to C has to be on the blue system of hyperbolas, and it has to be on the red system of hyperbolas. And it would have to be on a third system of hyperbolas between A and C, but I haven't drawn that one. And so, for instance, you can see this point over here has distance 3 to C, 4 to A, 5 to B, because it's a reflection of B. This forms a Pythagorean rectangle. So these 4 points do form an integer distance set, but it's a point formed by the crossing of one of these red hyperbolas and one of these blue hyperbolas. Now, it turns out that no two of these hyperbolas can coincide. The actual hyperbolas, the non-degenerate ones, have different axes. We have this horizontal axis for the red hyperbolas and this blue reflection axis for the blue hyperbolas. You have to be a little bit careful of the degenerate hyperbolas, but it turns out they can't coincide either. So for instance, we do get a line here as another degenerate case of a hyperbola. We get two rays on a parallel line for B and C, but they don't coincide. They're offset from each other. So with a little bit of case analysis that Erdős didn't do, he just said they're distinct. You can see that all of these hyperbolas are distinct. And if you have two hyperbolas, even the degenerate ones, two hyperbolas can cross at most 4 times. You can have at most 4 crossings for any two hyperbolas because they're quadratic algebraic curves, and curves of degree d cross O of d squared times. Here the degree is 2. There's 4 crossings, 2 squared. So that's essentially the proof. We have a system of d plus 1 by d plus 1 hyperbolas. Each pair of those hyperbolas cross 4 times. Those crossings are the only additional points that you can have. And so your point set has to have at most 4 d plus 1 squared points in it. Now I want to generalize this to other metrics. For instance, we might want to think about the L1 or L infinity metrics. I'm not going to be able to generalize to those metrics because in those metrics there do exist infinite sets of points with integer distances from each other, the integer grid. And so if I want to try to generalize this Erdős Anning theorem to other metrics, I need to be able to distinguish these metrics for which the theorem is just not true from the other metrics that I'm trying to prove it for. But there's another more fundamental obstacle to any kind of generalization, which is this idea of using the degree of an algebraic curve. Erdős uses this fact that hyperbolas cross a constant number of times. That is a basic fact about algebraic curves, but the algebraic curves that come up here are very specific to Euclidean distance. If we pick a different distance, we're going to get different curves, and there's no intrinsic reason to believe that they're always going to be algebraic curves. And so I would like to look for a different proof, a related proof, but a different proof, where I can use topological ideas rather than algebraic ideas. And so that's what I want to go through in the next few slides. Another proof of the same theorem for points in the Euclidean plane, but one that is based on topological and combinatorial geometry ideas rather than algebraic geometry, which is the basis of Erdős's theorem. And so instead of looking at the differences of the distances to 2 points, this hyperbola defined by the difference in distances from our unknown point x to A and to B, I want to look at the differences of the distances to 3 points simultaneously. The distance from A to x plus 1 in this case is equal to the distance from B to x is equal to the distance from C to x plus 2. And the plus 1, 0, plus 2 are specific to this example, but for any 3 points that I would choose to have integer distances to each other, and then any 4th point that is variable but at integer distances from all three. These distances from the fourth point to the other three are going to differ from each other by integers, because every distance in this imagined scenario is an integer, but by integers that are relatively small. They're bounded by the distances between these three given points by the triangle inequality. And if I have 3 points and I want to look at a fourth point that has some sort of equidistant property adjusted with these +1s and +2s from those 3 points, now we can use computational geometry, we can use Voronoi diagrams, because this fourth point, in order for these 3 distances to be equal, this fourth point has to lie at the vertex of a Voronoi diagram, at a point where these 3 Voronoi cells meet. This Voronoi diagram is the minimization diagram of these 3 functions, and it's just an additively weighted Voronoi diagram. We take the distances, we weight them by adding a small integer to each distance. We take the minimization diagram of those distances. We subdivide the plane into cells within which one of these 3 distances is the minimum. And the integer point that we're looking for is on the boundary of all 3 of these Voronoi cells. More importantly, it belongs to all of these cells. I'm going to think of a Voronoi cell as being a closed set. So the Voronoi cell of C is the system of all points in the plane for which C is one of the minima in this minimization diagram. This yellow cell contains its boundary. It's a system of points in the plane for which A is one of the minima. And so this green point belongs to the intersection of all 3 of those closed cells. And so we need to understand what is the structure of additively weighted Voronoi diagrams. I've written hyperbolic boundaries, by the way. These hyperbolas that bisect pairs of cells in the additively weighted Voronoi diagram for Euclidean distance are exactly the same hyperbolas that I had in Erdős's proof. In fact, I drew this figure reusing some of those same hyperbolas. So what properties do additively weighted Voronoi cells have? They're star-shaped. If some site, this blue site here, is one of the closest sites to this yellow point, a point in the Voronoi cell of this blue point, and you move towards this blue point on the closest curve connecting these 2 points in a straight line, the distance from the yellow point to the blue point as you move reduces by exactly the amount that you've moved, 1 to 1. If you move in any other direction, the distance reduces more slowly, or it might even increase. And that actually is a property that is not true of L1 or L infinity. In L1 or L infinity, there actually might be a continuous family of directions in which you can move and reduce the distance 1 to 1. But regardless, and this is actually still true of L1 or infinity, if you move in a straight line segment towards the closest site, it remains a closest site. Its distance decreases 1 to 1. The distance to all the other sites decreases at most 1 to 1, probably more slowly. And so this one remains closest. And so you have this property that if this point is in the Voronoi cell, everything on that line segment is in the Voronoi cell, and that's the definition of a star-shaped set. One complication is that Voronoi cells might not be two-dimensional. If I have a site Y, one of the generators of the Voronoi diagram, but that site, it has whatever additively weighted distance it has to itself, but it might have a closest neighbor that is not itself. It might be the case that it is tied with this blue point, for both of them being equal closest neighbors to this red site. And when that happens, what you get is a Voronoi cell for the red site that forms a ray extending away from the blue site. All of these points on this ray are equidistant from the red and the blue site. And then we might have a third yellow site Z that's equidistant from the red site and the blue site and from itself. And so its Voronoi cell is also a ray extending out in the same direction. And so we can get this nested system of Voronoi cells for collinear sites. And when we get a system of nested Voronoi cells like this, we actually get the number of triple intersection points of all of these triples of Voronoi cells can be infinite. And this is exactly what happens. This shouldn't be a surprise. This is what happens when you compute the additively weighted Voronoi diagram of the integer points on the real line embedded in the Euclidean plane, with the weighting system set up so that all of these points are tied as equally close. You simply make the weight of each of these integers be the negation of that integer, and you'll get a diagram like this. So this kind of degeneracy is something we have to worry about, something we have to watch out for. Non-degenerate cells in an additively weighted Voronoi diagram turn out to be interior disjoint. There's an argument about if they were not, if you had some point P that belonged to the interior of one cell and also belonged to another cell, then we could find this non-straight path that would have to be a shortest path, but that's an impossibility for the Euclidean distance. So 3 non-degenerate cells have to be interior disjoint, and then it turns out that they can have at most 2 of these triple intersection points. In a standard Voronoi diagram for unweighted distance, every triple of cells has 1 intersection point. In the weighted case, they can have 2. 2 is possible. You can get something that looks like this. But if you tried to form 3 cells with 3 of these triple junctions, the fact that these cells are star-shaped means that you could draw segments from each of these junctions to each of the sites. Those segments would all be disjoint from each other, and that would give you a straight line drawing of the graph K33, the complete bipartite graph with 3 vertices on each side, and that graph is not planar. So it does not have a drawing like this, and therefore these 3 junctions cannot exist. So any 3 degenerate cells have at most 2 triple intersections. Degenerate triples of cells, as long as they're non-collinear, we don't get that nesting effect that I showed you earlier. And so it turns out there's at most 1 triple intersection in the case where there's 1 degenerate cell inside another cell. Its Voronoi cell, the yellow Voronoi cell, forms a ray that gets stopped at the boundary between the blue and the red cells. And so this point where the ray stops is the 1 triple intersection of these 3 Voronoi cells. If you have 2 degenerate cells and they're not collinear, then their rays diverge and you get no triple intersections. So this gives us a proof of the Erdős Anning theorem, that if you have a system of non-collinear points with integer distances, then there must be O of d squared of these points, the same bound that Erdős proved. Because if you start with any non-collinear triple, if the points are non-collinear, certainly there's a non-collinear triple within them. Let d be the max distance between the points in that triple. Use all of the possible weightings where one weight is 0 and the other 2 are at most d, and that will give you a Voronoi diagram with at most 2 triple points. There are O of d squared weightings, and every point in your initial point set has to come from one of these diagrams with the weights given by the distances to the difference in distances between the farthest site to the given point and the other sites. And that'll give you a system of 3 weights where the weight to the farthest site is 0 and the other 2 are less than or equal to d. So it will be one of these Voronoi diagrams you've looked at. O of d squared Voronoi diagrams, O of 1 points per Voronoi diagram, O of d squared points in your given system of points. So that's a different proof of the Erdős Anning theorem. It maybe can be generalized more. So in order to generalize that theorem to other metric spaces, if we are using Erdős's proof, we need to understand the algebraic properties of these bisector curves, these curves that are equidistant from 2 points. For the new proof, you can tell it's a new proof because it needs different properties to be able to generalize to other metric spaces. The properties we need are that the metric space is a geodesic space. That means that the distance between any 2 points is the length of the shortest curve between those 2 points. The length of a curve can be defined as a limit of sums of distances of sequences of points along the curve. Using the notion of a shortest curve, we can define what it means in any of these metric spaces for points to be collinear. A system of points is collinear if any triple of them belong to a shortest curve. It turns out that what we need is not quite the fact that there's a unique shortest curve between any 2 points. That's true in Euclidean space. It's not true of some other spaces. But we don't want to allow these shortest curves to merge or split with each other at interior points. That property is going to be important in the detailed analysis of the Voronoi diagrams that we need to make this proof generalize. And in the Euclidean case, we're working with the topology of the plane. We used that topology in the fact that the graph K33 is non-planar. But we can generalize a little bit in that property. We don't need to be working on a surface that is spherical or planar, but we do need to have bounded genus. And the reason for that, at least for this proof, the reason for that is that if you have bounded genus, then there's a graph K3 something, 2G plus 3, that cannot be drawn on that surface without crossings. But the size of this graph that cannot be drawn without crossings is linear in the genus. So just as a quick example, this is a drawing of K36 drawn on a torus where you have to imagine that each of these hexagon edges wraps around from the top to the bottom, from the upper left to the lower right, from the upper right to the lower left. And so this hexagon, when you glue pairs of opposite edges in that way, gives you a topological torus. And on that torus, we have these three copies of this red point all get glued to 1 point, 1 red point and 1 blue point, 1 yellow point. The Voronoi diagram of those 3 sites, the red site, the blue site, and the yellow site, is the diagram that I'm showing here with 6 triple intersection points. So you can realize K36 on a hexagonal torus. You can realize it as the graph of Voronoi sites and Voronoi junctions on a flat hexagonal torus. And so trying to argue we don't have K33 on this topological space would not work, because we do have K33, we have K36, but we cannot draw K37 on this surface. There's an argument involving the Euler characteristic that shows that it would not be possible. So now we can start looking for metric spaces that have these properties, and we can prove, using exactly the same proof, I don't need to go through the proof again because it's the same, that all of these metric spaces obey an Erdős Anning theorem. All of these metric spaces have the property that every integer distance point set is either finite or collinear in this sense of collinearity. So to start with, I've been talking about L1 and L infinity. Let's look more generally at convex distance functions. These are defined from any centrally symmetric convex body, like this rounded rectangle, where you define the distance from some point to another point to be the scale factor that you would need for the body centered at one of these points to touch the other point. And that's a symmetric definition. If you scaled the same body centered at the other point by the same scale amount, it would touch. So this central rounded rectangle barely touches this point. These 2 points are at distance 1. Scale it by a factor of 2. These 2 points are at distance 2, distance 3, and so on. And if you start with a body like this one, where it's allowed to have sharp corners, it's not necessarily smooth, but it's strictly convex. That means that there's no line segment in its boundary. Then for these bodies, for these distance functions, the shortest curves are just the Euclidean line segment. And that's all we need to make this proof work. The Voronoi cells are star-shaped. They can be degenerate, but when they're non-degenerate, they're interior disjoint. The non-degenerate cells have at most 2 triple intersections because we're still dealing with the topology of the plane. The degenerate cases look exactly the same, and the proof works exactly in the same way and gives you the same bound on the number of points. For any system of points with integer distances, either they're all on a line or there are O of d squared of them. If you have a convex distance function that is not strictly convex, if it has a line segment in its boundary, then we can construct systems of infinitely many points at integer distances that don't look like they're all on a line and are not. So this is kind of an if and only if condition. If you're looking at a convex distance function, it obeys the Erdős Anning theorem if and only if it's a strictly convex distance function. We can apply the same theorem to the hyperbolic plane. The shortest curves are unique. They're hyperbolic line segments. They have all the same properties. We can apply it to surfaces of convex sets in 3D. And now you might think that this is trivial. If you have a convex set with bounded diameter, then clearly there can be at most a bounded number of integer points on it regardless. But this applies even when to surfaces in 3D that are unbounded. For instance, imagine this cone extending upwards infinitely far. This cone is locally approximately Euclidean, except at this one cone point. And the shortest curves on a cone, there might be more than one of them. If you have a point over here and a point diametrically opposite, there could be 2 equal shortest curves. But those shortest curves pass straight through each point in its locally Euclidean geometry, and therefore they cannot merge or split, which is all that we need to prove all of the properties that we need. At this one point that's not locally Euclidean, it's actually not possible for any shortest curve to pass through that point. You can originate a shortest curve from this point to any other point in the plane, in the cone, or vice versa, but a shortest curve between 2 points not at this apex does not pass through the apex. And so these surface metrics of convex sets in 3D have all the properties that we need, and any set of points with integer distances must either be finite or lie on a single geodesic on this surface. We can extend it to complete Riemannian metrics, which maybe you might be less familiar with. Roughly what I mean is the surface geometry of smooth surfaces. You can think of them as embedded in 3D, but they don't need to be. They're not required to be convex. They can have negative curvature. You can have surfaces that are torus or higher genus. But in order to make our proof work, because we want to forbid one of these graphs K3n, we need to restrict our attention to bounded genus surfaces. We need the Riemannian metric to be complete. Technically, this is defined as saying that all Cauchy sequences converge. What this means, for instance, is that in this cone surface, if we took away this apex point, if we punctured this surface by removing that one point, everywhere else it would have a nice Riemannian geometry, but it wouldn't be a complete Riemannian geometry because you can find a Cauchy sequence of points that converges to this cone apex, and any Cauchy sequence in a complete Riemannian manifold is required to have a limit point. And so to make it into a Riemannian manifold, you would need to add this point, but the geometry is not locally Euclidean here. And so you cannot make this punctured cone into a complete Riemannian manifold. But for a complete Riemannian metric of bounded genus, the same theorem applies with basically the same proof. Here's another example showing that completeness is a necessary property. This you can think of as being a cone with an infinite angle at the cone point instead of an angle less than 2 pi. Or another way of describing the same space is it's what you get using polar coordinates if you don't reduce the angle mod 2 pi and you think of two different angles that differ by a multiple of 2 pi as giving you different points. In this geometry, we can actually find an infinite set of points at unit distance from each other that are not all on a line. And so this tells us that we need this requirement that we look at a complete Riemannian metric. If we even allow one point of incompleteness, we can get a Riemannian metric where the Erdős Anning theorem does not hold. Okay. Now this idea of a unit distance set, it's a stronger notion, right? We're not requiring all the distances to be merely integers. They have to be all equal to each other. And that leads to an idea that I want to conclude with, the idea of, it's called the equilateral dimension of a space. The equilateral dimension is just how many points can you find at unit distance from each other. In the plane, you can find 3 points at unit distance from each other, the 3 vertices of an equilateral triangle. In 3 dimensions, you can find 4 points, the 4 vertices of a regular tetrahedron. And so the equilateral dimension of a space is defined as the maximum number of points at unit distance from each other. And so different distance functions are going to have different equilateral dimensions. The L infinity metric turns out to have equilateral dimension 2 to the d. The points of a cube or of a hypercube are all at equal distances from each other. You can scale that to be distance 1. The L1 metric has equilateral dimension at least 2d, because the points of a regular octahedron or a cross polytope all have distance 2 from each other, and you can scale that so they all have distance 1. This is actually an open problem. We don't know whether that is the equilateral dimension of this metric or whether there might be other sets of points that are all at unit distance from each other and more of them. But it's at least 2D. So in this paper describing equilateral dimension, attributing most of it to Robert Kussner, Richard Guy asks about the equilateral dimension of Riemannian manifolds, the same manifolds that we've seen here. And he asked, how many points at unit distance can you find on these things? If it's a topological sphere, the answer is at most 4. There are 4 points at equal distance on an actual geometric sphere, 4 points of a regular tetrahedron. You can scale that to have distance 1. You cannot find 5 because unit length geodesics cannot cross each other in a Riemannian metric. If 2 curves of unit distance crossed each other, you could shortcut the curves near the crossing geodesics. So the equilateral dimension of a topological sphere is 4. The dimension of the surface plus 2. And Guy asked, is that true in higher dimensions? Now, if you look at Riemannian manifolds of unbounded genus, we can form Riemannian manifolds that have unbounded equilateral dimension, essentially by taking this graph of K3 joined to K4, joined to K5, joined to K6, joined to K7, etc., and thickening all of those vertices and edges into little spherical surfaces connected by thin tubes. And if you do it in carefully enough, you can find a point on each of these spherical surfaces, adjust the lengths of these tubes so that all of the points in each of these graphs are at unit distance from each other. And so you have 3 points at unit distance, 4 points, 5 points, 6 points, 7 points at unit distance, unbounded numbers of points at unit distance from each other. But then, if you have this system of spheres and tubes all connected to each other, you can imagine embedding it in 3-dimensional space and then filling in the gaps remaining in that space so that you get a 3-dimensional Riemannian manifold where the material you fill it in, think of it as being like honey or like glue, like something that is very slow to move through, so that the distance that you would travel to move through these interstitial spaces between the tubes is much longer in the intrinsic metric of the 3-dimensional Riemannian manifold that you get. And so that all of the shortest paths are the ones that stay on the tubes. And so you can embed this example in a 3-dimensional Riemannian manifold that has just the familiar topology of 3-dimensional space. Or you can embed any single one of these examples in a single Riemannian sphere of 3 dimensions. And so this answers Guy's question in the negative, that topological spheres of dimension D with a Riemannian metric do not have bounded equilateral dimension. The equilateral dimension of a sphere can be arbitrarily large, and the equilateral dimension of a Riemannian manifold that has the same topology as ordinary 3-dimensional space can give you a single manifold where there are arbitrarily large integer distance, unit distance point sets. Okay, so that's more or less all I wanted to say. The main conclusion I want to draw from this is that an elegant proof, Erdős's proof, certainly is elegant. He published it in 5 lines. It's not the same thing as a flexible proof. And by making a proof that is a little bit longer because there's more details to unpack with respect to the Voronoi diagrams and their properties and their degenerate special cases, we get a more flexible proof that applies to a huge continuous family of infinitely many metric spaces. Now in the paper, I don't have in these slides, but in the paper itself, you can improve the d² bound on the number of points that you get in a non-collinear integer distance set to O of d for a strictly convex distance function and O of d to the 4/3 for a convex surface. That still doesn't match the sublinear bound that we get for Euclidean spaces based on algebraic methods. But the other direction that I'd like to extend this further is 3 dimensions or higher. And in particular, a question that I don't know is the Erdős Anning theorem true for three-dimensional hyperbolic space? Is it the case that any integer distance set of points in this specific space is either finite or collinear? I don't know. I would like to know. Okay, that's it. The rest of the slides are just credits and references. So I will